we'll call it one part.
Welcome back to NE 630, nuclear reactor analysis for nuclear reactor theory, of course. So last time we started a topic of how to homogenize the heterogeneous reactor so that we would be able to solve the diffusion equation, the one-speed diffusion equation. So the one-speed diffusion equation, the coefficient of the fluxes and the derivative of fluxes, as you remember from before, if you try to write the one-speed diffusion equation, this is dphi by dt 1 over velocity is equal to Laplace square phi multiplied by d minus sigma absorption phi plus nu sigma fission plus the source. So those parameters, nu, sigma fission, sigma absorption, and d, we consider them as space independent. What do you mean by space independent? It means that we consider them as homogeneous. How we reach to this conclusion? This is one speed. Again, we average over space and we average over what? Over energy. Because usually those are a function of what? Space and energy. So one speed means we average over energy. One homogeneous means we average over space. So how you average over space? Last time we talked about the fact that if you have, let's say, fuel rods or fuel rods like this, and in between the fuel rods you have here, this is the fuel, and this is the moderator, for example. Then you have to homogenize this, and last time we said that we will take a unit cell and try to look for the flux ratios so that we would be able to look for a value for the homogenization, for the cross sections and so on. So we stopped last time at a definition of the thermal utilization, and we said that the thermal utilization is for a heterogeneous reactor or a heterogeneous cell is given by sigma absorption in the fuel multiplied by the average flux in the fuel multiplied by the volume of the fuel divided by whatever absorbed everywhere. So sigma absorption in the fuel, average flux in the fuel multiplied by volume of the fuel plus sigma absorption of the moderator, the flux in the moderator multiplied by the volume of the moderator. Of course, if you have a, let's say, clad or structural material, you will have all the absorption here in the rest of those materials. But let's assume that we have fuel and moderator system only, and we are not talking about structural material, or we are talking about clad or anything. So this is just the definition for the heterogeneous, because it is just distinct fuel elements in a moderator like. Then last time we showed that this equal to sigma absorption in the fuel multiplied by the volume of the fuel divided by sigma absorption in the fuel, volume of the fuel plus sigma absorption of the moderator, volume of the moderator. And all of this will be multiplied by sigma absorption of the fuel, V fuel, plus sigma absorption of the moderator, V moderator. So what we did is we multiplied upstairs and downstairs by the same quantity. And this one has sigma absorption of the fuel, V fuel, plus sigma absorption of the moderator multiplied by the V moderator multiplied by this Xc. So what's this? This is just the homogenized cross section for the homogenized F. So this is F homogeneous, as if you blend everything and you homogenized everything. So this is F homogeneous. So F heterogeneous, So F heterogeneous is equal to F homogeneous multiplied by this ratio then. So now how we will measure this thermal utilization? So there is a way to measure this thermal utilization, and the way to do it is, first of all, you will have very large, let's say very large moderator. Yes, go ahead.
On the F net, is that V?
This is not net. This is F heterogeneous.
Is that supposed to be V energy on the
Keep the operator's walk straight and eliminate any discomfort associated.
Okay, thank you. So how we measure this thermal utilization? So measurement of F. So when you have the fast energy here, a neutrons, let's say a neutron start from the fission, it will have collision, one collision, another collision, and so on, start doing multiple collisions until it reaches to the thermal energy range, and this is 0. So then it will go inside and thermalize inside the thermal energy region. So as you remember from a couple of lectures back, we define slowing down density, slowing down and we said that this is slowing down density in the moderator. What does it mean, slowing down density? If you remember, it's number of neutrons slowing down beneath, let's say the thermal energy region, or beneath any energy of interest, if this is Q of E M in the moderator. So number of neutrons slowing down past certain energy per centimeter cube per second. So it's not like the flux is per centimeter square, this is per centimeter cube. So if you have, let's say, a large volume of moderator and you have a source of neutrons inside, or a fission, let's say fuel inside, and there is fission, so neutrons coming from the fission fast, they will start emerging from the fuel, getting into the moderator, slowing down until they reach to the thermal energy region. So if you want to do the thermal neutron balance in the moderator, so if you want to do the thermal balance of the neutrons, thermal balance of thermal neutrons in moderator. So the balance will be Qm is how many neutrons are slowing down into the thermal energy region per centimeter cube per second. If I multiply this by the volume of the moderator, this will give me the total number of neutrons per second slowing down in the thermal energy region. But I have to multiply this by 1 plus L square B square G. And what's this is, this is the non-leakage probability. So this means of those reaching to the thermal energy region here, I multiply the total number that will reach up to the thermal energy by the non-leakage. This will give me the fraction of those neutrons that will survive leakage and will be thermalized. They will be in the thermal energy region here. So this number here should be equal to sigma absorption in the moderator, phi in the moderator, volume of the moderator, plus sigma absorption in the fuel, phi in the fuel, average volume of the fuel. So what does it mean? It means that the neutrons that slow down from the fission energy and reaches to the border of the thermal energy region, they must, if they will escape from being leaking from the system, they must get absorbed in the fuel, either in the fuel or the moderator. So this is just what this formula says. So in this case, again, as the definition of F that we just stated here, sigma absorption fuel multiplied by V fuel average, V fuel, divided by sigma absorption in the fuel, V fuel, V fuel, plus sigma absorption in the moderator, V moderator, and V average moderator. So we can define, we want to calculate this F, the thermal utilization. So we can get the ratio QM as a function of X, a position, over phi moderator as a function of X. So what we will do is we'll get a very large, let's say, very large moderator, and inside the moderator we will put indium foil. So we'll put indium foils. So those foils will put sit foil. Let's say the foils are like this. So we will put in the same location an indium foil, which is, let's say, it's a bare foil. It does not have anything to cover. And we will put at the same location, let's say, we will separate this by a bar of any material that's not, for example, it has very low or minimal absorption cross-section, for example. Then we will put on top of those in the same location, we will put the indium foil wrapped inside. So this is, all those are indium foils. Indium foils. And then we will cover the indium foils in another set with cadmium. So this is indium covered with cadmium. So those are indium covered with cadmium. So you will have indium covered inside cadmium. Why we are doing this? Because indium has absorption cross-section and it has a resonance just above the thermal energy. So the thermal energy cutoff is 0.1 or 1, let's say 1 electron volt. Let's say the thermal cutoff, or 0.1 electron volt. So the indium has absorption cross-section above the thermal cutoff, resonance absorption cross-section. So the cadmium usually has a very good absorption for the thermal neutrons. So what will happen for the cadmium? When you cover the indium with cadmium, everything but the thermal will be transferred or transported through the cadmium to the indium, and you will prevent the thermal from penetrating the foil itself. So we did this indium foils will see everything. The cadmium wrapped indium foil will see only the epithermal, which is the total minus the thermal flux. So those foils will see everything. What does mean everything? It will be activated to A total. But those foils, they only see the epithermal flux only. So the activation for the wrapped indium foils will be A epithermal. So if I want to get the activity for the thermal, all what I want to do is just subtract the epithermal activity from the total activity. This will give me the A thermal. So again, if you want to get the slowing down density and the flux, for example, you will assume that the slowing down density, which is the total number of neutrons, they are slowing down beneath the thermal energy region. So you expect that this slowing down density, the activity will be proportional to the slowing down density. And what activity here? Is the epithermal. Yes, because the slowing down is everything coming from the fission and getting into the thermal energy region. Yes, and this is the definition of the epithermal. So the definition of the total flux is everything from the fission up to zero. Thermal flux is everything in this region. Epithermal is everything in this region. So the slowing down is proportional to the activity in the epithermal cadmium wrapped foil. So you can remove the proportionality and put C epithermal coefficient called C epithermal multiplied by the activation of the epithermal, and then you can get the flux in the moderator, which is the thermal flux, because the flux here in the moderator is just thermal flux, and it is proportional to just the thermal activity, which is this one. I can remove the constant again. I put C thermal multiplied by A thermal. So now, if you get the ratio of Q M in the moderator divided by phi M, and both as a function of X, for example, this will give you C epithermal divided by C thermal multiplied by the activity in the epithermal divided by the activity in the thermal. This ratio here, they call it cadmium ratio. So this is well known, cadmium a well-known ratio for cadmium. Then now, if I want to know what's the flux, the epithermal flux in this case is proportional to the slowing down. If I want to know this, I have to know cadmium ratio is already defined value from tables. You will know what's the cadmium ratio. It's well-known ratio for cadmium. But I have to calculate this, C epithermal over C thermal. So what you will do is you will come and put something like an array, and in the same place you will put, of course I did not show them at the same place because I cannot overlay the cadmium wrapped and the bare one on the same place. I cannot put in the same place on the blackboard. But what you will do is you will put a cadmium wrapped indium foil, for example, and at the same place of this place you will put just a indium bare indium, and this is bare indium, and this is cadmium wrapped. Cadmium wrapped. And again, you will do the same, but for long array. So you will have cadmium wrapped, bare, cadmium wrapped, bare, and so on. You have long array, so you will have a distribution with X, assuming that this is the X axis, and you will do this experiment. So we will assume that we will have a moderator, and inside this moderator we do not have any fuel. So you will have a tank that has moderator only, there is no fuel, and you will know that in this moderator you will have a source of neutrons coming from the nuclear reactor. Q is how many neutrons per second. Some source Q that emits, let's say, n neutrons per second. You will get the neutrons in a neutron per second inside this tank, where you have a large array of cadmium wrapped and bare indium foils, and then you can look at the neutron balance. The neutron balance is sigma absorption. The only absorption that will take place in this tank will be only on the moderator. So there is no absorption in fuel. There is no fuel. So I will have only just a water, and the only absorption will be in the moderator. So sigma absorption in the moderator multiplied by the flux as a function of X. This is X direction multiplied by dx, and you will integrate over this. So those total number of neutrons absorbed in the moderator is just equal to the slowing down density integrated over X, and this is just equal to Q. So if you have a source of neutrons, total number of neutrons 1 million. Then what you will do is you will say those 1 million, if they do not leak from the system, and this is a very large moderator or something like this, and you will neglect leakage, you will say they will slow down, and you will have a slowing down density. So if you get this slowing down density and you integrate it over the distance, this will give you number per centimeter square, and this is also number per centimeter square per second. So, and this number that slows down, it must end up being absorbed in the moderator, and this is the number of absorption inside the moderator per unit area, which is equal to the same number of neutrons that you started with. which is in this case is the source. So why we are doing this? So you will notice that if you want to calculate rho, and rho is just equal to A thermal, the activity of the thermal, because you will just get the ratio, which will be A thermal as a function of x dx multiplied by C just to get the ratio, rho will be equal to the ratio of the flux to the Q of x dx to phi of x dx. So this will be A thermal of x dx over A epithermal of x dx. The ratio of the activities, let's assume that rho is the ratio of the activities, A thermal over A epithermal, and this is the total activity in the thermal energy over all the line here, and this is the total activity over all the line for the epithermal. So for the bare one, you will get the total activity, A total, as a function of x, and from this one you will get A epithermal as a function of x, because here is x equals 0 up to x, let's say, equal to 100. So this is the epithermal activity, this is the total activity. When you subtract the A total as a function of x minus the A epithermal as a function of x, this will give you just the A thermal as a function of x. So we got this from the experiment. So those two, I will take the ratio of those two and I will call it rho, and then you knew that A epithermal is equal to Q divided by C EP I, and A thermal is equal to Q of x. So you can just substitute here with C epithermal phi of x dx divided by C thermal of Q of x dx, and then what's these two ratios? Where can I get the ratio of the flux to the integrated flux to the integrated slowing down? Where do you think? Look in the blackboard. Here. What's the ratio between phi of x divided by Q of x? So Q of x over phi of x is just equal to what? Q capital over sigma absorption, or 1 over sigma absorption. Yes? So this ratio is equal to what? 1 over sigma absorption in the moderator. So you will end up rho equal to C EPI over C thermal multiplied by 1 over sigma absorption in the moderator. So now we were looking for C epithermal over C thermal, which is this ratio. And again, we can get this ratio from here. Rho, from the experiment, you will be able to measure this term, and you will be able to measure this term. Here it is. Those two activities you will be able to measure as a function of x. Then integrate. Integrate means sum. Integration means summation, because you do not have a continuous variable, you have discrete variable. So you will sum. Integration is summation. So you will sum the activities in the thermal and you divide it by the epithermal. This gives you what? Rho. So rho now is known. Sigma absorption in the moderator is known. So this value of C EP over C thermal is known, and now you can define your F as 1 minus sigma absorption in the moderator, phi moderator multiplied by 1 plus L square B square M divided by QM, and this is just 1 minus L squared P squared divided by rho cadmium ratio CR multiplied by the flux M divided by the flux M as a function of X. So this is just the definition for F that you measure. The experiment is poorly written in the book. So if you follow what's written there in the book and what I did in the blackboard, you will be able to grasp it a little bit more. So now, we knew now how to do the homogenization for the cell. So what is the major reason behind what we are doing right now? So in order to design a nuclear reactor, you have to solve, let's say, in order to design a, let's say we assume that our nuclear reactor will be a rough estimate, we will solve a diffusion equation. Of course, you do not do this in designing a nuclear reactor. We will solve a diffusion equation, one speed, and the uniform parameters like sigma efficient, sigma absorption, U, and everything. But you have your reactor is heterogeneous. So what do you want to do? First of all, you will get to the cross sections and average over energy, so that you will get average over energy. You will get single speed. Yes. Then once you get single speed, you need now to homogenize your heterogeneous reactor to transform it from heterogeneous to homogeneous. So what I did last lecture and this lecture is just I'm showing you a method of homogenization the nuclear reactor. So how to homogenize it? You have to take into consideration what? The effect of the depression of the flux inside the fuel, which we call it what? What's the phenomena of depressing the flux inside the fuel?
Self-shielding.
Self-shielding. So you have to take into consideration the self-shielding, and I showed the self-shielding. Now we will come up to a new factor that I have to take into consideration, and this factor is called local Bauer peaking factor. Local Bauer peaking factor. And what happened is we will define a ratio called FPP, or peaking Bauer factor. The peaking Bauer factor, Bauer peaking factor. This is Bauer peaking factor, and this comes from F is a factor, PP is Bauer peaking. So the FPP is just equal to the maximum flux or maximum power. We'll show that it is the same. Maximum power, for example, in the cell divided by the average power. But we knew that the power is proportional to the flux. Yes. How the power is proportional to the flux? What is the power in the nuclear reactor? Fission rate multiplied by what? By a constant. What is the constant? Energy per fission. Yes? So it is just energy per fission. It's a constant integration of sigma absorption of X, P of X, dx. Yes? Over volume. Yes? So the power is proportional to what? To the flux. So power is proportional to some proportionality factor multiplied by a flux. So this will be the maximum flux. And this will be what? The average flux. So this is the same. This is the same to say this is the maximum flux to the average flux, for example, because they are related between each other. So if we look at a cell like last time, this is just the fuel, and this is the moderator here, and this is another fuel here, and another fuel here. And let's assume that I will take the cell to be here, fuel, part of moderator, half of the moderator, and half of the moderator. So if you look at the thermal flux will be something like constant inside the moderator somewhere here, then it will drop inside the fuel, and it will have something like symmetrical shape inside the fuel like this. So this the derivative at this point is just d phi by dx is equal to 0 because you have a minimum. And let's assume that this thickness here is 2a. So half of it is a and half of it is a. And let's assume that the moderator region here, the thickness of the moderator region is b. And you knew that d phi by dx at b is equal to 0. Also, why equal to 0? Because the flux in the moderator, actually, the flux in the moderator will be like this. And so on. Yes, guys? So the flux also in the moderator peaks out at what? Peaks out at what? At B. So the flux d phi by dx at x equal to b is also equal to 0 because the flux is maximum. Yes?
Would you want to call it b plus a?
No, I just take b from this the border of the.
All right.
Or maybe I take b to be from the center here. So flux at b. So b from the center to here and a from the center to here. Okay, guys? So this will be then b minus a. The moderator region will be b minus a. So now I will find a way to calculate this peaking factor, and I will show you that this peaking factor gets into some of the formulas that we need in order to homogenize our system. So the power peaking factor is given by this, and I can now calculate an effective fission cross-section in the fuel, and this effective fission cross-section is just sigma fission in the fuel. In the case of the homogeneous case, again, when we do the homogenization, we notice that we have what? The heterogeneous part is equal to what? Homogeneous part multiplied by what? Multiplied by this factor from last lecture, Vm divided by Vf divided by 1 plus Xa multiplied by Vm divided by Vf. Do you remember this when we make it last time? And we said that Vf homogeneous, what's the Vf homogeneous? Sigma fission fuel homogeneous is just equal to sigma fission for the fuel multiplied by V fuel divided by what? V fuel plus what? V fuel plus V moderator. Yes? This is the normal way. We said this is the way to homogenize if you do not have to take care about self-shielding and everything. Just multiply by the volume fraction, and this is just homogenizing the number density. Okay, guys? So how to calculate this power peaking factor? So in order to calculate the power peaking factor, we have to calculate the maximum what? Maximum flux over what? Over the average flux. So we have to solve the diffusion equation in those two regions. Again, to obtain the flux in the fuel and the flux in the moderator, and then average over the flux in the fuel and get the flux and the maximum flux and so on. So it will be the same hassle. So phi average is just the average flux in the fuel multiplied by the volume of the fuel plus the average flux in the moderator multiplied by the volume of the moderator divided by volume of the fuel plus volume of the moderator. And this is if you take the average flux in the fuel as a common factor, this will give you 1 plus Xa Vm over Vf divided by 1 plus Vm over Vf. So what you did is, I'm not talking about the slab case, I'm talking about cylindrical case. So in the cylindrical case, this is a exaggeration. So if you remember last time, I showed you this. Yes, guys? And I told you that this is what? This is the contra rod. And each one of those is what? Assembly. And each one of those assembly, it has hundreds of fuel elements. Yes? And in between the fuel elements, there's moderator. So I took one of those and I just magnified it to be like this. So this is just one of these. So this is the fuel, this is the moderator, this is imaginary surface here. So what you did is, you have your fuel, you have your moderator around the fuel, you blend it together, but in this case, it's not in the Brown blender, but it's in a nuclear blender that will take into account the flux, the pressure, and everything. Then it will produce an equivalent cell that's homogenized. It has blending fuel moderator mixture, and this takes into account what? Takes into account the flux, the pressure, and takes into account everything, self-shielding and everything. Okay. So when I did this, this is the way to do the averaging for the flux now. The averaging is the flux is the average in the fuel multiplied by the volume of the fuel, and the average in the moderator multiplied by the volume in the moderator, and then you will do this. So this is the average. So the power peaking factor is just sigma fission in the fuel multiplied by phi in the fuel at A divided by sigma in the fuel fission effective multiplied by phi average. Okay, how this? Okay, this is the power peaking factor. Where is the maximum power, do you think? Look over there. Where is the maximum power?
Halfway between fuel rods.
No, I'm talking about in the fuel now. Because there is no power production in the moderator. Yes? I'm talking about power. Yes? So power is just sigma fission multiplied by phi multiplied by constant, which is what? 200 MeV per fission. I take it off from both upper and lower side. So where is the maximum? If you look here, you will notice that the flux here is minimum, but the flux here is what? Is maximum. So it is the flux in the fuel at X equal to A. Look at over there. It is the flux in the fuel at X over what? A. So this is the maximum one. Yes? And how to calculate the average? Just to get the average what? Over there. Sigma fission multiplied by flux what? Average flux. Okay, guys? So here is this one, and this will be equal to what? We knew what sigma fission. We knew what sigma fission effective. And sigma fission effective, we got it from where? And why we said it is effective? Because we have to blend this and homogenize it and bring it here. Yes? So we got the sigma fission effective. If you multiply it by this average flux, it will give you the average power in the cell. Yes? But the maximum power in the cell, even if you blend it and make it one homogeneous cell like this, the location of the maximum power was the location of the maximum flux at the what? At the surface of the what? Surface of the fuel. Okay, guys? Then when you do this and substitute here, you will get phi F at A divided by phi average F multiplied by VF plus VM divided by VF, and this will give you phi F at X equal to A divided by phi average of F1 plus VM or V over VF. What's this ratio? VM over VF. Moderator to what? Moderator to fuel ratio. Now, all what you will do, and instead of solving this again, we solved it last time. Yes, You remember last time when I homogenize a slab geometry, I solved the diffusion equation inside what? Inside the fuel. And I solved the diffusion equation inside the moderator. And I stated clearly last time that the moderator has SM term. And somebody asked me and I told him this is the thermal neutrons inside the moderator because there is no thermal neutron source inside the fuel. And we solved those and we got ugly. I told you it's ugly two equations, phi and phi. You will go back to the book, look for those two equations, then substitute with x equal to A so that you will be able to get the flux at x equal what? To A. And then take this equation, and you know that you are very good in math, and then integrate it over x over the to get the average or the flux average in the fuel. Once you do this, you will obtain very nasty equation, very bad one. And then this is what you will get. FBB, the power peaking factor, is just FA, FM, phi F at A over phi average of F multiplied by 1 plus V moderator divided by VM, and this is equal to 1 plus VM divided by VF multiplied by A divided by LF multiplied by the cotangent of A over LF. And A is the distance or the thickness of half thickness of the fuel. So if A over LF, what's LF? Diffusion length in the fuel. If your fuel over the diffusion length is less than pi, you can simplify or whatever FBB will be equal to 1 plus VM over VF multiplied by 1 plus 1/3 A over LF square 1 divided by 45 A over LF to the power of 4 plus blah blah blah. Okay guys, so this is how to get the power peaking factor once you homogenize your cell. Again, to reiterate, I will not go through the control rods because the control rod will take also big part of the lecture. So maybe next time I will get to the control rod, how to do the control rod. But just to reiterate from the beginning, from early beginning, I said we want to design. This course is not a design course for nuclear reactor. Why we study this course? To help us understand what is the reactor physics. I told you at the very early beginning, the first lecture, if we want to design a nuclear reactor, you can solve the transport equation, a subset of the transport equation, a simplification of the transport equation is the diffusion equation. But the diffusion equation, you have to make it called, you have to solve the so-called multi-group diffusion equation, that you will solve this formula, the diffusion equation, but you will make groups of energies. In the thermal energy region, the most important part in thermal reactors is the thermal energy region. So I will divide this energy region to be 1,000 groups. So I have to solve thousands of those equations. Each one of those equations has energy bin, an energy region from 0.001 electron volt to 0.002 electron volt, and so on. So you have to solve this equation. Okay, we are not in the welfare yet to do this in this course, so I have to show you how to solve the diffusion equation. In order to solve the diffusion equation has what? Cross sections in it, nu, the multiplication factor, and so on. To understand what's nu, sigma fission, blah, 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 we studied chapter 1, which was what? Cross sections. So we show what do we mean by macroscopic cross section, microscopic cross section, what do we mean by multiplication factor, what do we mean by F, eta, epsilon, P, and all those stuff. Then we drove the diffusion equation. And we said, okay, we will not solve the multi-group diffusion equation, we will solve only one group. In order to solve one group, you consider that, oh, but I have a Maxwellian distribution of the neutron, a 1 over E, then I have a chi distribution, how I will collapse everything and make it only one speed. So we stated that, okay, you will average your nuclear properties, sigma, d, nu, everything, you will average it over what? Over the energy and get only an average value for everything. So average sigma absorption, average sigma fission, average nu, average d, average blah, blah, blah. Then blindly, we solve the diffusion equation, and we stated that when we solve the diffusion equation that this is homogeneous properties. It came to us last couple of lectures that, oh, how we knew that this is uniform properties. We do not know. So we have to rethink, oh, our nuclear reactor is not homogeneous. It's actually made of heterogeneous reactors. So now, how to transform this heterogeneous reactor into what? A homogeneous one. To do this, we have to do homogenization. I told you that the best way to do homogenization is to homogenize the number densities just by multiplying by the volume fraction. The fuel occupy this volume, so I multiply by this volume fraction. The moderator occupy this volume, I multiply by the volume fraction. But I showed to you that if I want to do this volume average, is not good. Why is not good? Because this will not take into consideration some phenomenon that took place while the reactor is homogenized, and among those phenomena is what? Self-shielding. So we have to think about, okay, how to calculate the self-shielding. Then what we did last time is we get to solve the diffusion equation in a unit cell. And this is why we said, okay, we will look for a unit cell. And the unit cell is just one of those. Okay? So we look at one of those unit cells, and then I will take it and I blend it, crunch it, and make it something like this. Then each one of those unit cells, it will be identical to this one. Maybe when you come near to the clad, to the structural material of the assembly, here in this location, there is fuel, there is moderator, but there is also structural material. So you have to take into consideration the absorption and the structural material and so on. So you will have different types. This one is very near to a control rod. Yes? So if it is very near to a control rod, there is another way of homogenizing this one because you are near to a control rod and so on. So you will replace all those by now something like this. A homogenized cell here, a homogenized cell here, a homogenized cell here, here. So you can use the diffusion equation in each one of those places using a finite difference scheme, and it will be very easy because all the properties here is the same. Here is the same. Here is the same. Oh, here is near to the let's say to the structure. So maybe it's homogenized, but maybe a different value. So I will have something like constant. Maybe I have something like this at the edge. Maybe, or something like this. Then next lecture, I will talk to you about, okay, we homogenize everything like in the fuel and moderator. What we will do with the control rod. We have also to do what? Homogenization for the control rod. But the control rod, it's a little bit difficult. Why? Because the control rod, I cannot solve easily the diffusion equation because it's a very high absorber. But with certain assumption that I will say, oh, okay, if this diffusion length L is very small compared to, let's say, or very large compared to the dimension, I can consider this as a one-dimensional problem. Then I can use the diffusion equation to support me and be able to solve the diffusion to calculate at the end some homogenization for what? For the control rod. Now I homogenize the control rod. So now I have what? I homogenize everything in the core. Then I can use the diffusion equation and I say, okay, here is the solution, just finite difference scheme for numerical analysis, and I would be able to use it very simple in the core. And this is called cell calculation. Okay guys, this homogenization is the cell calculation. Then once you solve the whole diffusion equation model in the core, is called core calculation. So there is cell calculation and core calculation. And this is usually how this is trivial, this is simplified, this is very simplified picture. The global picture, if you want to do more of this, it's in upper level courses in neutronics and stuff like this. But this is just, I'm trying to show you what we are doing, where we are in the course. After this chapter, we will now, in order to do this homogenization, you have flux, yes, that we homogenize. So when we homogenize, the energy sigma average of energy is equal to what? Sigma sigma absorption as a function of energy E, phi of E dE divided by phi of E dE. Okay. When I will do the homogenization for energy, I need what? I need a flux. How you will get a flux before solving the diffusion equation? The diffusion equation is nabla square phi plus blah 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 blah. So you solve the diffusion equation to get what? To get the flux. We did not solve the diffusion equation. How I will get a flux to homogenize? This will be the chapter, the next chapter, that we will say, okay, now let's study the slowing down and thermalization in the nuclear reactor. So we knew that we have this flux in the first region, and 1 over E in the epithermal, and then the Maxwellian. So when we study next chapter, we will know that this is the distribution of the neutron. Then we can use something called a weighting flux. So this weighting flux will get this value. So we'll use this weighting flux to average what? The cross section. Take this cross section in the what? The fusion equation. Solve it. Get a real value for the flux. And then take this flux. Do the homogenization again. And then get the new value. Give it back to the same diffusion equation. Get the corrected flux. And do the iteration until you reach to the what? The correct flux. And once you reach the correct flux, that's it. Then after this chapter, we'll be able to solve what? The time-dependent diffusion equation to see what's going on with time and how the fuel will burn up and burn up calculation and so on. And we will conclude with types of reactors. I'm just giving you the global picture, where we are and what we are doing and everything like this. Do you have any question? Yes.
When will we get our homework back?
Hopefully, I hope. If not Friday, it will be Monday. But I will upload the solution so that everybody will review it before the exam. I will try to upload the solution tomorrow or after tomorrow. Okay, guys, do you need anything else? Have a wonderful